Howdy folks. In this video we are going to learn how to use arrays in Visual Basic, and to provide ourselves an interesting problem to solve we are going to use numeric integration to compute the area under a curve shown here in our plot. So what we have here is two columns of numbers, x and f of x. And if you look at the code, or at the formula for the f of x column, you will see that f of x is equal to x squared minus 2x plus 12. So this is just a little, it's a parabola basically, a quadratic equation. Conceivably you could put any kind of function you want in here. But for now, that's the function we're using, and we're going, x varies between 0 and 8, and the points in our, so each of these rows represents a pair of coordinates, if you will, an x and y coordinate, where f of x is the y coordinate, and we've plotted that on a xy scatter plot over here on the right. And our objective is we want to approximate the area under this curve using the trapezoidal rule of numerical integration. So before we get into that, we need to do a little bit of a review on numerical integration. So basically, to take the area under a curve between two numbers x1 and x2, we calculate the integral from x1 to x2 of f of x times dx. And of course, you know, that's the polynomial, the equation that we're using in this case is pretty simple. You could, if you dust off your calculus skills a little bit, you could integrate that and just plug it into the solution to the integration and have your answer pretty quickly. But we're going to solve it using numerical integration. And the concept of numerical integration is that you may not know the underlying curve. You may just have some data. Or maybe it's just a really complex equation, and it's not, you know, it's not a trivial exercise to integrate that, and so you need to do something a little more sophisticated. And so with one of the ways to do that, which you probably learned in beginning calculus class, is to use the trapezoidal rule. And with the trapezoidal rule, we take this distance, or this length between x1 and x2, and we divide it into a number of equally spaced segments. And then for each of those segments, that defines a trapezoid where the two sides are parallel and vertical, and then, you know, we have a linear segment here and a linear segment at the bottom. So we're approximating our curve here with these linear segments, and the thinner you make these trapezoids, the smaller these segments, and the more closely a linear interpolation of those points approximates the actual underlying smooth curve. And so if you calculate, it's pretty trivial to calculate the area of the trapezoid. So if you split the curve into all these trapezoids, or the area under the curve, I should say, and then calculate the area of these trapezoids and add that up using this summation, you then will have the area under the curve. And so if you look at each individual trapezoid, the width of that trapezoid is xi plus 1 minus xi. The height of the trapezoid is just the average of these two f of x values. So f of xi plus f of xi plus 1 divided by 2. And the area then is equal to the height times the width. So you take the height and multiply it by the width, and you now have the area. And so that's the area of a single trapezoid. And so if you want to get the area under the curve, you sum all of the individual trapezoids. So you go, I goes from 1 to n minus 1, f of xi plus f of xi plus 1 over 2 times xi plus 1 minus xi. And so Go back a little bit. You'll notice that we went, the summation goes from 1 to n minus 1. That's because, assuming n is the number of individual x values along this route, you want to start here and you want to end here, because you're going to look at x and then x of I and then xi plus 1. So in other words, if we have 10 individual x values, that gives us 9 trapezoids. So we have to keep that index. We have to pay attention to the indexing when we go to solve our problem, and I'll come back and talk about that later. But so basically, we are going to use Visual Basic arrays to solve this problem, and we're going to do that in a multi-step process. So to begin with, step 1. Declare 2 arrays using the ReDim statement, just big enough to hold the x and f of x values. Traverse through the table, copy the values into the arrays. So this table happens to have 17 values, and we've actually keeping track of that using the count function. So we just say equals count B6 to B29, and so that tells us we have 17 points, and I'll explain why that's significant in a minute. But conceivably, we could have more points in this. For example, maybe we want to extend that a little bit. We're going to start out with that. The point is, we want this to work no matter how many points we have in this curve, in this table. And so what we're going to do is we are going to write a loop. We're going to declare 2 arrays, one for x and one for f of x. And then we are going to start a loop at loop 2, or at row 6, and we're going to loop down until we find an empty cell. We're going to copy these 2 columns of numbers into the 2 arrays that we just declared, and then we're going to write another loop that executes, or that solves this summation using those arrays. Okay, now that seems a little complicated, but it's not too bad. So alright, let's dive in and start solving this. So I'm going to double click on the compute button, and we're going to say option explicit. So we're going to need to declare some arrays, and we're going to say dim my row as integer. We're going to need a row counter. And then let's declare another variable called n, which is the number of points. And then we're going to say n equals range n PTS. And so basically, this means that this cell right here, we've named it n PTS. And so we're going to read that number using this range statement. We're going to store that in n. That gives us a nice simple variable to reference when we want to know how many points we have. So then the next thing we're going to do is we need to dimension 2 arrays just big enough to hold all our points. And to do that, we're going to use the ReDim statement. We're going to do x 1 to n as double. And then we're going to do ReDim, we'll call this one f 1 to n as double. So we have just declared our points. Excuse me. We've declared 2 arrays just big enough to hold the points here, 1 to n and then 1 to n. So now we're using the ReDim statement because that allows us to dimension the arrays using a variable. If you're going to dimension them using constants, use the DIM statement. If you're going to dimension where one of either the lower or upper index on the array is a variable, then you need to use the ReDim statement. And that allows us to dimension these arrays to exactly the size we need. We don't have to guess beforehand how big they need to be. And so now we're just going to say, we can use a for loop here. Yeah, I mentioned earlier that we were going to loop until we found an empty cell, but we can do it a little more elegantly than that. We're going to say for I equals 1 to n, and then let's say x equals cells. And so the first item is in row 6, and so if we take the, but I is going to start out as 1, so if we say the row is I plus 5, then I think we should have it. So in other words, we're going to iterate, I is going to go from 1 to n, it's going to go from 1 to 17, but to get the right row, we need to read this value from row 6. So if we just take that integer I and we add 5 to it, that'll tell us what row we need to read that value from. And the x value is coming from column 2, and the y value is coming from column 3, or the function value. So I'm going to say f equal, I'm just doing a little copy paste here. So that should load up our arrays into our values into the x and the f arrays. Now before we continue with our coding, let's test that. So I'm going to go to the I'm going to add a watch for x, and let me scoot this over here. Let's see, let's reposition that. So we have x, and then I'm going to add another watch for f. Okay, so now we're going to go in here, and we're going to jump into this with the debugger, exit design mode, and it says variable not defined. Aha! Well, that's true. I haven't declared a variable. So let's declare I as an integer. And then now you'll see in our down here in the watch window, it allows me to now let's see, I'm going to try something tricky here. I am going to see if I can reposition that up here to where we can see those values. There we go. So they're these are the x values, and these are the f of x values. And I'm going to just start hitting the F8 button, and we'll cycle through here, and we get a type mismatch here. Why type mismatch? Now that is reading. Let me see if I've got my indices correct. I'm kind of stumped here. What is the value of cells I plus 5 comma 2 0? Oh, all right. Very simple problem here. I neglected to put the indices on my arrays. So yeah, that makes sense. I'm trying to write something into the array without giving it a proper index. So all right, let's try that again. So now it should work. And okay, now our code is correct, and we're loading the values in. So as I'm cycling through here, you can see these values start to populate over in the array. And we're basically reading those numbers from those two columns of cells. And we're just going to keep iterating all the way down to the bottom. I is currently at what? Excuse me, I is 15. 16, 17, and done. So there we go. So that seems to work okay. And then we get to the end of that loop. Let's just do that again. When you get down to here, F and X are both fully loaded with these same two vectors or columns of numbers that we have here. So now, why did we do that? Why not just do our calculations by reading the values from the cells? The beauty of using arrays, by copying them into the arrays, now we can index these arrays, x and f of x, by using an index that goes from 1 to 17. Hopefully I'll remember the index next time. And that should allow us to do our calculations in a format that very closely resembles this formula right here. So now we're going to write a second loop where we calculate the area incrementally by calculating the area of each of the individual trapezoids formed by pairs of x values, and adding that up, and when we get to the end we'll have the area. By adding in the area of the individual trapezoids, we'll have the entire area under the curve. So let's give that a shot. So now we're going, let's exit that run mode there. So we're going to declare a new variable, which is the area is a double. And then we're going to say for I equals 1 to n minus 1. Now let's go down here and do next. I like to finish my loop before I worry about the middle part. So what we're going to do now is we're going to say area equals area plus. So we're going to calculate the individual increments of the area based on that trapezoid formula. Let me close that watch window for a second. And that was equal to f of x, f of I plus 1. No, let's do f of I plus fi plus 1 divided by 2. Now that should give us the first part of this. Let's see, this right here, f of xi plus f of xi plus 1 over 2. Now we're going to multiply that by xi plus 1 minus xi. So let's jump back here. I'm going to put another set of parentheses around this just to make it really clear. Times xi plus 1 minus xi. And let's see, I think that should work. So this is the height of the trapezoid, and this is the width of the trapezoid. And every time through the loop we're going to calculate the area of the trapezoid, the current trapezoid, and add that up to our, and incrementally add that to our area value. And so basically this little loop right here represents this summation right here. We're looping from I to n minus 1, and we're adding things up every time through the loop. We're calculating this value and adding it to our sum. So our last thing to do would be to, let's see, go back to here. We want to put the solution in F10. Okay, so we'll go back to the code. We'll say range F10 equals area. And we will cross our fingers and hope we did everything correctly, and the answer is 203. Let's increment that a little bit. 203 exactly, or pretty close. Now, is that the right answer? I don't know. Let's go look and see. If you this is our function, x squared minus 2x plus 12, and so basically we want to calculate the integral going from 0 to 8 and of x squared minus 2x plus 12. If you integrate this equation right here, you get x cubed over 3 minus x squared plus 12x, and you evaluate that between 8 and 0. And so if you plug that in, the 0 part is 0. So if you plug in the 8's, you get 8 cubed over 3 minus 8 squared plus 12 times, I should say 8 right there. equals 202.67. So just the actual value is 202 1/3, but we're getting 203. But that's okay. This is numerical integration. It's meant to be approximate. And so that's pretty close. And if we were to break this up into smaller increments, go from 0 to 8, but instead of using 17 values, use maybe 100 values or something, we'd get an answer that's much closer to that. In fact, we can, if you want to, let's see if we can quickly test that theory. So let's go down to 31. Let's just double the number of points. Go to 34 points. And we're, instead of incrementing in 0.5, or 0.5, we'll increment in 0.25. And so I'm going to drag that down. Let's see. So we're going to go from 0 to 8. Whoops. 0.25, 0.5, 0.75. Let's see. Well, we went one too far, so let's delete that row. So now we have, let's see, our count function needs to go all the way down. So now we have 33 points going from 0 to 8 by increments of 0.25. And now, when you redo that calculation, we get 202.75. So before we had 203, and now we have 202.75. The true answer is 202.67. So 202 and 2/3, excuse me. So as we can see, this is working correctly. And again, if we go back and look at the code here, the beauty of using arrays, by copying these cell values into the arrays, it allows us to then do the calculations in a fairly simple and an intuitive fashion that very closely mimics the algebraic equations that we had here, or the integral here, and representing this summation. And so that's it. In the end, it's not that many lines of code, and ends up being a pretty powerful little tool here. We could plug in pretty much any algebraic equation we wanted to here, and this would properly approximate the integral over that range. And that concludes this video. Thanks.